Hello everyone, and today we're going to be looking at linear combinations of random variables. So this is part of the statistical inference, part of the specialist maths course. When we think of a particular group of data, so presume for us a minute that we collected the minimum and maximum temperatures in Melbourne in a particular month and year. We can represent that on a graph as shown below. So based on this temperature, we're able to calculate the average temperature, our mean, or we can also consider that to be our expected value, E of x, and we can calculate the standard deviation. Remember that the standard deviation, if we square the standard deviation, we get the variance, which is another measure of spread, and we can represent that as the variance of x, where x in this case is denoted as being the temperature in degrees Celsius. So we've got this information shown, we've been able to calculate the mean and the variance. If we instead wanted to represent these temperatures using degrees Kelvin, another measurement, what we would need to do is to add 273.15 to each measurement. So what we're doing is, and this is important to note, is that we are not changing the actual data points. So these data values are still the same as they were before. We haven't altered them, or rather we haven't altered the distribution of them. By adding each of these values, all that we have done is translated them. So the distribution is identical, it's just the average that's changed. So all that we've done is move this over. So that means that our average here, our mean, or our expected value, has become what we had earlier on, our 9.8 that we had initially, and we've added on this 273.15. The standard deviation hasn't changed, so we notice that the variance is the same as it was before. So what we've created here is really a new random variable, and I could call this new random variable k, for example, and our new random variable is equal to our old random variable x plus 273.15. What that means is that E of k is what we should have said instead of E of x. E of k is equal to this value here, 9.8 plus 273.13, and the variance of k is actually the same as what we had before. It's the same as the variance of x. We can notice that because the spread of the data is the same. Once again, just to reiterate, all that we have done to the data points is move them. We can move them by 273.15. We've converted to another unit, so we've changed the location where it was, changed where the center was, but we haven't changed the actual data that we've collected. We haven't collected new data, we've just converted it to a different unit. So we have talked about how this will affect the mean and the spread of the data. Now look at changing scale instead. So we still have our min and max temperatures like we had before. So as we had earlier, we had this defined as being x being the temperature in degrees Celsius, and our E of x, our expected value, is 9.8, and our variance of x, remember, we get by squaring the standard deviation. What we're going to consider now is if we were to multiply the temperatures by 2. This is perhaps not a straightforward example to understand, because why would we multiply something by 2? But if we think of another example, if I had collected a group of measurements, a group of lengths, for example, that were initially given in centimetres, change of scale would be if I had to multiply each of them by 0.01 to convert to meters. So that's also an example of change of scale. We're sticking with the temperature example for now, and we're just saying, let's say I was to multiply each of those data points by 2. I get a new spread that's being shown here. So the initial spread, we haven't multiplied all values in this case, just some of them to get an idea. We can see that if I had my initial set of data given here on the left, the shape of this is the same, because remember, we haven't collected new data, we've just taken our old data and multiplied by 2. We can see that in this case, not only has the mean, the expected value changed, it's moved over here, but also we've got the spread of data has changed. So we're considering both of those things in this case. So what this means when we're thinking about it here is that when we're getting our new value here, sorry, just let me change the colour for a minute, there we go. When we get our new values here, our E of 2Z, as it's called here, what we do is we take 2 and we multiply it by E of Z, the initial value. With our variance of 2Z, what we're doing is we're going to square the 2 and multiply by the variance that we had of Z. The reason we're squaring it, just bear in mind that the actual formula for calculating variance, which isn't something we need to do by hand in a specialist maths course, but if we were wanting to calculate variance, we do it by taking the sum of the difference between any particular x value and the sample mean and squaring it, and then we divide by the sample size minus 1. So just keeping in mind the fact that we're using squared values to calculate variance, that will give you some indication of why we've got a squared value here, but we're not going to get into the proof of it right now. We can also consider changing scale and location. So once again, we've got our data, this has been collected. This time we're going to convert it according to a particular linear formula, sorry. So here's our linear formula we've got for converting it to Fahrenheit. We multiply by a scalar and we add a constant value here. Notice that we are not collecting new data, we are simply taking our old data and converting it into a new unit. So we're converting units is often what we're doing with this kind of question. When we're having a look, we can see that the average temperature given here has changed and the standard deviation has changed as well. So we've got a new average and a new standard deviation in this case. We can combine this in a number of formulas, and these are formulas that are given on your formula sheet. So this first one, we've already looked at this before, saying that when we've got a linear combination, the scale factor here, we multiply it by the mean of the original data, and then we can add on our change in location. So this is the change in scale, we're multiplying every data point by a particular value, and this is a change in location. So we're adding B to every data point. If we were to add together two independent random variables, x and b, we can work this out according to the following formulas. One thing to note here is that these values a and b, they are just to do with essentially changing the units or changing the scale as we were talking about before. So it is not about changing the data, we're not collecting new data. Each of these two random variables are separate, and if we're multiplying it by a or b, we're changing the units or the scale. We can work out the variance the same way, and we've got this second formula that we can see here. Once again, remembering that this A and B is to do with changing the scale or the units that we've got going on. So let's look at a few examples, because there are questions that are very similar to this in the exams, and there are also questions that appear similar but are actually quite different. So this first one here, we've got patients in a hospital ward are taking vitamin C and D. Their doses of the two vitamins are shown in the table below. I haven't included the table because it isn't relevant to our calculations. It's believed the consumption of vitamin C and vitamin D by patients are independent random events. That's important that they're independent. CX is recorded in milligrams and DY is included in micrograms. So we've got different scales here, milligrams and micrograms. So when they need to figure out the total amount of vitamins taken, T, we do need to add together X and Y, but we need them to be in the same units. So what we have currently is that we're trying to add together X milligrams plus Y micrograms. So we have to be converting that. They do give us a useful piece of information down the bottom here, that 1 microgram is equal to 10 to the negative 6 G. So we know 1 microgram is equal to 10 to the power of negative 6 grams. You should also know that 1 milligram is equal to 10 to the power of negative 3 grams. Or that to convert to from grams to milligrams, we divide by 1,000. So if we're combining this together, hopefully you can see that when we combine these two things together, that 1 microgram is equal to 10 to the negative 3 milligrams. I want to make sure that both of my vitamin measurements are in the same units, so I'll convert both to milligrams. So this is where we get X plus 10 to the negative 3 Y, or, as is given up earlier, 10 plus 0.001 Y. Now we can use the formulas that we've just worked out to find the mean and variance for T, because all that we've done here is change the units, or change the scale. We've combined two separate random variables, and our scale factor that we're looking at, that in this case is this 0.001, this scale factor here, it's converting from micrograms to milligrams. So all that we're doing is we're taking the mean and the variance we already had and changing the units. So then we can use those formulas. If I want to find out the expected value of T, what we need to do is to take our expected value of X and add to that 0.001 times the expected value of Y, using that formula from earlier. So we will have E of X, our 3.9032, plus 0.001 times E of Y, which is 121.71. Notice that if we hadn't multiplied by 0.001, it wouldn't make sense to do this multiplication and addition. We'd be trying to add two values of different units. You can check this on your calculator, and we will get 4.02491. We then have a look at the variance of T, and we can use that same formula before, A squared times E of X. There's no coefficient of X, so it's just going to be variance of X, plus B squared, which in this case is 0.001 that we want to square, times the variance of Y. We substitute in values. Once again, you can check it yourself, but we get this answer here. I've said it a lot, but I want to reiterate again, these formulas work because what we're doing is changing the scale. We are not changing the initial values that gave us that mean and standard deviation. We're not actually changing the spread of the data or the mean. We're just changing the scale that it was measured on. This past exam question shows another case that's actually appears similar but is different. So if we read this one, a dairy factory produces milk in bottles with a nominal value of 2 litres per bottle. To ensure most bottles contain at least the nominal value is like the nominated or the named volume. It's how much they're telling people we have. So we can think of nominal value as being the named volume. The machine that fills the bottles are normally distributed with a mean of 2005 and a standard deviation of 6. We're going to ignore question A for a minute because that's not what we want to focus on. Bottles of milk are packaged in crates of 10 bottles, where the nominal total volume per crate is 20 litres. We want to work out the mean and standard deviation for this particular crate. Now, some of you might think if we let X equal volume of milk in one bottle, most of you are going to be tempted now, I think, to say that to work out the standard deviation, that we're going to get a new variable. If we've got 10 bottles, we're going to say we want to work out 10x, and E of 10x equals 10 times E of x, and variance of 10x equals 10 squared times variance x. That's going to be your temptation, but that is incorrect. We can only use these formulas that we had here if we're just changing the scale or changing the units. That's not what we're doing in this case. In this case, we're taking 10 bottles, 10 different bottles, and each of those 10 different bottles is going to vary differently. Each of those 10 different bottles will have a mean of 2005 and a standard deviation of 6. So each of those bottles are going to vary in a different way. We can't use that formula we had before because we're not changing the scale. What we're doing is we're working out what happens 10 times. So instead of using that formula, what we're doing is that we're going to work out the chance of each bottle individually and then put it all together. So what we do in this case is that to get the mean, we just say, okay, I'm going to have the mean initially was 2005, and I need to multiply this by 10 because I would expect this 2005, we can also call that the expected value. We would expect each bottle to have a mean of 2005. Because we've got 10 of them, we can multiply by that. And this is how we're then going to get our answer that we were looking for, which is 20,050. If we're looking at our standard deviation, we can't really work things out straight away from standard deviation. So we take our standard deviation, which we had initially was 6. If we convert this to variance, the variance of one bottle is 36. Each bottle has this same variance, but we've got 10 of them. Each 10 will vary by 36 milliliters, so we multiply by 10. Each bottle varies by 10, so we get 360, which will give us the standard deviation we were looking for of 6 square root 10. So once more, in the first case that we were looking at, where we use the formulas shown here, that's where we were only looking at creating one new situation, and we were changing the scale. So we were taking our mean and our variance from earlier on, and we were changing the units that it was measured in. In this case here, the units aren't changing. What we're doing is that we're saying we've got the mean and the variance for a single bottle. We're going to multiply by 10 because we want to see what happens when 10 of them vary. We haven't changed the scale. What we've done is we've looked at comparing one bottle and then changed it to 10 bottles. So it is an important distinction. Whenever we're looking at having 10 different things, then we're going to follow this method that you've seen here now. Let's have a look at another couple of examples just to clarify this idea. So in this question, we have to figure out which method are we going to use. The first one, is it a change of scale of units? Or the second one, have we taken one randomly distributed item and multiplied to get a number of them? So the local supermarket sells apples in bags that have negligible mass, so no mass essentially, small enough that we don't worry about it. The stated mass of a bag of apples is 1 kilogram. The mass of a particular type of apples is known to be normally distributed with a mean of 115 and a standard deviation of 7. So this is when we're dealing with one apple. A particular bag contains 9 randomly selected apples, and we want to work out the probability that 9 apples has a total mass of less than 1 kilogram. Because we're talking about 9 randomly selected apples, that implies that we've got 9 different apples that we're dealing with here. So what we're going to say is that if I was to let M equal the total mass, when I'm working out the expected value or the mean, what we're doing is we're taking the mean of one apple and multiplying by 9. This is not a change of scale. Each apple that we've got, each of our 9 different apples are going to have different values, but each of them, we could expect the weight of each of them to be 115. So that's the expected weight. So the expected weight of 9 of them when we multiply will be 1035. The variance, each of those apples is going to vary with a standard deviation of 7 or a variance of 49. So each apple is going to vary with, will have a variance of 49. But we've got 9 of them, so the total variance for 9 of them, if we multiply by 9, is 441. So we get that M is normally distributed with a mean of 1035 and a standard deviation of square root of 441, although we do put the variance in here for our notation. We're wanting to work out the probability that our 9 apples, M, have a total mass of less than 1 kilogram. Our other units are in grams, so we have to say less than 1,000. You then put this into your calculator. You'll use normal CDF, enter the lower value of negative infinity, the upper value of 1,000, the standard deviation of square root of 441, and the mean of 1035, and the answer that you will get is 0.0478, which is option A. In this next question here, if we're reading what's going on, a farmer grows oranges and lemons. The oranges, so our oranges have a mean mass of 200 grams, so the mean of our oranges is 200 grams, and the standard deviation of our oranges is 5 grams. The lemons have a mean mass of 70 grams and a standard deviation of 3 grams. We assume the masses for each fruit are normally distributed, and we want to know what is the probability, and correct to 4 decimal places. So what is the probability that a selected orange will have at least 3 times the mass, at least, so greater than or equal to 3 times the mass of a randomly selected lemon. So this is what we're looking at here. Now we've got a few things to consider when we're going through this, because this is where it's going to get a little bit tricky. We've got a whole lot of things going on. We've got 3 times the mass of a randomly selected lemon. What we're doing this time, this 3 times the mass of a randomly selected lemon, means that we're changing the scale. We're taking our mass of 1 lemon and multiplying by 3. So we're only looking a lemon, 1 lemon. It's different to the previous question where we had 9 different apples. This time we've got 1 lemon and we're multiplying its mass by 3. So we're changing the scale. So if we wanted to come back to our lemons here for a minute, if I'm working out E of 3 lots of the lemons, 3L, my formula is 3 times 70, so I would get 210, and variance of 3L would be A squared, 3 squared, from our multiplying the lemons by 3, times the variance of a lemon, which is 9, and we get 81. So now if we think about what's going on, we need to look at our actual situation here. So we're wanting to know, another way of writing this probability is the probability that O minus 3L is going to be greater than or equal to 0. So we need to work out the expected value and the variance for these things. So the expected value of O minus 3L, what we do is we take E, the expected value of oranges, and we're going to minus 3 times the expected value of the lemons. So we will get 200 minus 3 times the expected value of our lemons, which is 70, which will give us negative 10. And if I want the variance of our O minus 3L, we're going to get variance of O plus negative 3 squared variance of L. So we will get 25 plus 9 times 9, which will give us an answer of 106. Once again, the reason we can use these formulas is because we are just changing the scale. We're taking 1 lemon and multiplying it by 3. It's changing the scale. We are not getting 3 different lemons. So now that we know this, we know that our O minus 3L distribution is normally distributed with a mean of negative 10 and a variance of 106, or a standard deviation of square root of 106. We can once again use normal CDF. I'll just scribble over here for a minute. So we're still going to use normal CDF. We want to know the chance that O minus 3L is greater than 0, or greater than or equal to 0. So we're going to put our lower value into CAS as being negative infinity, our upper value into CAS, sorry everyone, let me just go back a minute, that's not correct, is it? So our lower value is going to be 0, our upper value is infinity, our standard deviation is square root of 106, and our mean is negative 10. We enter this into CAS, the answer we get is 0.1657, which is option C. I have said it a number of times, but there are two different types of questions you can come about to here. You need to ask yourself, are you changing scale, like we are here, having one thing that is varying and changing the scale of that, in which case we can use these formulas? Or if, as in the previous question, we have multiple things, multiple items varying, then we just need to simply multiply by however many of those items we have. If you have any questions, feel free to ask, and I hope this has been helpful.